Hello everyone, this is Professor Bob and this is Discrete Mathematics for Computing. So, welcome to class, if this is what class is nowadays, right? This is what I have in store for us today. Now today we're going to talk more about z-scoring and probability, or what we can do is we can mathematically model the probability of a certain event happening in general. Now, you know how I am with definitions. I'm sure you could Google it and come up with something else, but you know how I feel about Google too. Just the fact that you can recite facts doesn't mean you're necessarily knowledgeable on something. So we're going to cover z-scoring today. And now I have z-scoring in 2 short lectures. So you're going to get z-scoring 1 today, and you're going to get z-scoring 2 at another time, because I want you to digest these one at a time. It's important for me to know that you do that, because I think that's definitely a path to success. Now remember what z-scoring is. What z-scoring is it is a way that we can mathematically model the probability of something happening. Now how do we do that? Well, we do that by looking at our past results or our past observations, putting together a descriptive model of what happened, specifically the mean and the standard deviation. And based on that, we can make a prediction on the probability of an event happening in the future. For example, let me go down to the next slide here. Let's take a look at the following example. Now what I did here is I have the same slide, but on the right-hand side I have 2 descriptive measurements. We have what? We have the mean, right, which is mu, or me, depending on your dialect, is 75. And let's just say these numbers represent test scores on the right-hand side. So let's just say we have... you are a teacher at our esteemed college here, and you have 1,000 students. So 1,000 students take your final exam. It's a big class, right? Much bigger than this one. So we have 1,000 students that take your final exam, and we have a mean score of 75. 75 what? How about just 75? It could be a percent, it could be points. We have 75 units. Again, it really doesn't matter what it is, but we have a mean score of 75. Now, based on that, we took a look at the standard deviation. We came up with a standard deviation of 5. Now, I'm assuming at this point you know the formula for a mean and you know the formula for a standard deviation. If you don't know how to come up with a mean or a standard deviation, please stop the video now and figure out how to do it, either by looking at a prior video or some of the reading that I suggested. But anyway, I'm assuming you know how to do this. And as I pointed out previously, all of these things that we do as far as predictive math are based on descriptive math. And if we don't know how to do something, we can't go on to the next step. So I know I'm repeating myself a little bit, but it does warrant repeating. So anyway, so we have a mean score of 75 with a standard deviation of 5. Now, using the empirical rule, which I'm assuming you already know, we can make some assumptions about our test scores. Now, if our test scores are evenly distributed, right, we have the following. The empirical rule tells us that 68.3% of our results are going to be within 1 standard deviation of the mean. 95.4% of our observations are going to be within 2 standard deviations of our mean, and 99.7% of our observations are going to be within 3 standard deviations of our mean. Now this is important because observations are past observations and observations that have not occurred yet. What does that mean to you? That means future. That means that we can use the empirical rule to mathematically model events that haven't happened yet, or predict a future either incorrectly or incorrectly, but it gives us a mathematical model in which we can do so. And it gives us a way that we can mathematically model future events, or what we call predictive modeling. So anyway, so based on those numbers, if you look at within the curve, we get percentages. Now, all of them add up to about 100%. If you go from left to right, basically we get roughly, with some rounding, we get 100%. So we basically say that 34.1% of our observations are going to be either at our mean or one standard deviation below or above, right? 13.6% of our observations are going to be between either one standard and two standard deviations. Say that 10 times fast, Bob. I'm not feeling well today, so I apologize. Below our mean, or 13.6% above our mean. And it also says that 2.1% of our observations will be between two standard deviations and three standard deviations, either below our mean or above our mean, or 0.15% of our observations, either past or future, will be three standard deviations or more below our mean or above our mean. Now, this is important because you can make some generalizations about this. Number one, how about this? True or false? Any result that we have that is more than three standard deviations above our mean or below our mean are unusual. True or false? True. It says here, our empirical rule says that only 0.15% of results will be three standard deviations above, or 0.15 will be three standard deviations or more below. Okay, so let's have another one. A result, again, let's remember our standard deviation is 5 and our mean is 75. So we could say a future result of 76 could be a common result. Again, I'm doing this in general terms, or painting with a broad brush, as you say, on purpose. So how about this? True or false? A future result of a student getting 76 on an exam is common. True. We could say here that it is very common for something to be with, for example, 76 would definitely be within one standard deviation of our mean here, which is 5. Standard deviation is 5. So using the empirical rule, that would be a common result. So let me expand this a little bit more. And again, notice I'm having you think in general terms here. Let's just say we get a student that gets a test score of, how about this, that is more than 3 standard deviations below our mean. More than 3 standard deviations below our mean. So again, I'm not putting a number on it. I'm just look at the standard deviations here. So more than 3 standard deviations below our mean is 0.15. So if Billy gets a score that is more than 3 standard deviations below our mean, that's a very unusual result. Not unheard of, right? But unusual. That doesn't happen a lot. Why? The empirical rule tells us so. The empirical rule says the odds of Billy having a test score that is more or at 3 standard deviations below our mean are 0.15. Very, very small. Okay, so what? Okay, but how about this? Billy and Bobby, I'll use B's. Billy and Bobby and Bonnie, Billy, Bobby, and Bonnie, the 3 of them are in our class. And the 3 of each of them, have a score that is 3 standard deviations or more away from our mean of 75. True or false? Is that a common event? False. It is not common. Okay, another question. True or false? Is that insanely uncommon? True. It's very insanely uncommon. For us to have 3 students that have a test score that is that low is very, very uncommon. Now, what does that tell us mathematically? Again, remember, I try to kind of put this in context. I'm the math professor for people that don't like math. I try to spin this into some real life analysis. In real life, I would look at this and say, Billy, Bobby, and Bonnie, there's something going on there. What is the reason why the three of them in my class have those scores that are so far away from the mean? This might help me identify a few things as a professor. It might help me identify maybe there's a common thing between Bobby, Billy, and Bonnie that is making them score so poorly that I need to address, or maybe something else. Now let's change this a little bit. Let's change the scenario. We'll still use the same numbers. We'll use 75 for a mean with the standard deviation of 5. So let's just say 75 was the electric bill. I'll just go on some recent experience I have for doing some mathematical modeling for a very, very famous electrical company in the area, not to mention any names. Exelon, right? Did I say that out loud? Let's just say 75 is the average electric bill. Okay, so Billy has an electric bill that's more than 3 standard deviations from our mean. Is that common? I'm just going to speed things up. No, it's not common, because if there's a bill that's more than 3 standard deviations above our mean, that's fairly uncommon. Not unheard of, but unusual. Again, I'm speaking in general terms. It's unusual, right? Because 3 standard deviations or above our mean, there's only the odds of that happening are 0.15. Why? The empirical rule tells us so. Now, let's say Billy, Bobby, and Bonnie, right? Each of our 3 customers have electric bills that are more than 3 standard deviations above our mean. Now, again, I'll pose this as a true or false question. Is that insanely, again, speaking in general terms, non-mathematical terms, is that insanely unusual? True. That is insanely unusual. The odds of Billy, Bobby, and Bonnie, say that 10 times fast, each of them having an electrical bill that is more than 3 standard deviations above our mean of $75 is very unlikely. Now, what does that tell me, right? Think about it. It could mean that maybe there's a common thread between them. Maybe they're running 25 refrigerators. Maybe they got 85 big screen plasma televisions from 1995, which, by the way, use a lot of electricity. So basically what mathematical modeling of the future and the past allow us to do is they allow us to look at these different data sets and kind of perform further analysis on them. Now, remember, just coming up with the answer of, yes, true, it's very unusual, is really half of what we do in the real life. Because in the real life, after we put a mathematical model together, the other half is, okay, well, now what do we do about it, right? They don't teach you that in math class, in the high school, and unfortunately at the college level, we don't do that. I don't think we do a good job of doing that, where we just, you get the answer. You're like, oh, well, yeah, it's 0.15723. Okay, well, what does that mean? Remember, I'm the guy that tries to help you put this in context, so maybe even if you don't enjoy math, you understand why we use it. All right, so let's move on a little bit. Let's go to the following scenario. We got our student here, Angelina, on the right, okay? Now, Angelina on the right is a student of ours, and let's put some context to what we got here. We're still going to use the same numbers. We'll still use 75 for our mean, and we'll use 5 for our standard deviation. So Angelina is in our class, and she's going to take our test tomorrow. So bear with me on this. So this is yesterday. Remember Albert Einstein, that the future is only a past event that hasn't occurred yet. Okay, so Angelina hasn't occurred yet. So let's go back to yesterday. So yesterday, we look at our test scores. Now we have 1,000 kids. I call you all kids. I know you're not, but it helps me cope, right? We have 1,000 kids in our class and 1,000 scores on our exam. And the mean score is 75 with a standard deviation of 5. So this is what it would look like. using the empirical rule and using our distribution. 75 is in the middle. It's our mean, right? So 50% of our observations are going to be below our mean, and 50% are going to be above. You already know that. So I put some numbers here on what we have for 1 standard deviation below and above, 2 standard deviations below and above, and 3 standard deviations below and above, right? So 70 is 1 standard deviation below, 65 is 2 standard deviations below, and 60 is 3 standard deviations below. And the converse for, our standard deviations above the mean. We have 80 being 1 standard deviation above our mean, 85 being 2 standard deviations above our mean, and 90 being 3 standard deviations above our mean. All right, so this is what we see today. Tomorrow, Angie turns in her test, and she gets a 94. Or how about this? Let's just say, let me just backpedal. We're going to give Angie a test tomorrow, okay? And we're going to give Angie a test, and Angie tells us, okay, she says, you know what, Professor Bob and esteemed other officials of our university, I am going to get a 94 on the test tomorrow. And she asks us, so what do you think about that? Right? We're putting this in a conversation. And we say, okay, Angie, you're going to get a 94? Oh, let us take a look at it. So, we look at this and say, we look at our descriptive model, and this is it. You're looking at our descriptive model without the yellow X. We look at our descriptive model, and we're like, Angie, what'd you say you're going to get? And she says, I'm going to get a 94. So what we do is we plot that in the distribution. 94 is, and again, speaking in general terms, it's more than 3 standard deviations above our mean. Heck, it's almost 4 standard deviations above our mean. Almost 4, right? All right, let me ask you this, true or false? Would that be unusual for Angie to get a 94? You bet it would. You'd say, Ange, wow, man, you're going to get a 94? The chances of you doing that on their test tomorrow are way less than 0.15. Now, that's where z-scoring comes in. Now, remember, I'm only giving you the general idea here. With z-scoring, you could put an exact number on this. I haven't shown you that formula yet. I'm going to do that, in coming up. I'm just trying to sell you on the general idea. Because remember, if you don't know the general idea of z-scoring, the formula is going to mean nothing to you. All right? Remember, you need to feel it. You need to know what this means. So Angie would say, wow, so if I get a 94, that's really unusual. And we wouldn't tell her in, mathematical terms, but, we would say, well, I guess we could. I don't know if she understands z-scoring, but we could say to each other, so what do you think about that? And we would say to each other being, math professors or mathematical modelers, we'd say, wow, man, we're trying to make a prediction on an event happening tomorrow that might be 4 standard deviations above our mean, just under it. That's not very, very likely, which would be true. All right. Now, as I said before, I'll show you how to do this with a z-score and give an exact number, right? But trying to sell you on the general idea. I know I just said that, but I said it again, right? Brittany, whoops, I did it again. All right, so let's take this one step further. So Angie, let's just say and I don't got a slide for this, so just bear with me. I'm almost done. So tomorrow happens. And Angie takes a test, and we'll stay with A's. And Angelo takes a test, and Al takes a test. So Angie, Angelo, and, oh God, what was it? And Al, Angelo, and Angie, the three of them, using a Chicago accent, you guys, the three of you guys, right, take a test. Angie gets a 94, Al gets a 95, right? And what was the other one? Angelo gets a 92, right? I'm just picking these numbers up. You can write them down if you want to. All right, I picked, on purpose, 3 numbers that are higher than my standard deviation. And the X here that you see above the 90 is what Angie's score is. And I don't have a slide for this, but let's just say we plot Al's score, which is, more than 3 standard deviations or whatever it was, and we plot Angelo's score, And that's more than 3 standard deviations too. So the three of them turned in their test, and all of them are 3 standard deviations or more above our mean. What does that tell us? Well, putting together the predictive model, if we did it yesterday, we would look at this and say, oh my gosh, it's like the odds of that happening are almost nothing for the 3 of them to get a score that high. So I would look at a few things. I would say, okay, why did they score that high? Did they know each other? Did they study together? Maybe they cheated, or maybe they didn't. But what happens is that this model that we put together helps us drive these decisions. Before we knew about this, we just would say, wow, man, the 3 of you did really, really good. We might look at them on the positive level, say, wow, man, you 3 are onto something. How in the world did you score so high on this? Well, let's find out. Or on the negative level, you guys cheated. Or for some reason, the 3 of you found some way to game the system and get unusually high scores. It could be either or. I'm not saying it's one or the other or somewhere between. But what I'm saying is we can be driven by mathematical models that help us drive these decisions, either in academia or in business. What if these were, again, electrical bills? And then the mean electrical bill was $75, and all of a sudden we got a cluster of bills that are above 3 standard deviations. Why is that? Maybe there's an electrical failure. Maybe there's a transformer failure that is delivering too much electricity to their house. Maybe they got a meth lab. I don't know. I'm trying to be realistic and say that there's reasons why we could do this. Now, you see this sometimes. You see this lately where you'll see COVID maps and you'll see hotspots. What is a hotspot? Well, a hotspot is something like this. There is mathematical modelers that look at these things that say, why is it that there is so many more COVID cases in this specific area? There is a reason for it, and we are going to find out. Or the converse. Why is it that there are no COVID cases in this area? I mean, we could look at metro areas, and there's a hotspot of COVID in one spot, and 3 neighborhoods away, there is the same number of people, and for some reason, the results are different. It's like, wow, there's nothing here. You are like 2 to 3 standard deviations below the mean, or in some cases 4 or 5. So you get people from the Center of Disease Control or from pharmaceutical makers that are studying all this stuff. Again, politics aside, I mean, real scientists and mathematicians that don't vote one way or the other way are looking at these things and trying to make determinations of why things are the way they are based on predictive models and mathematical modeling. Now, the empirical rule and Z-scoring are just 2 simple ones. Now, there's other ones that are used as well. More on that a little bit later. Again, I'm kind of wrapping things up here. The purpose and the objective of what I was doing here is I'm trying to link together the empirical rule with Z-scoring without showing you really the formula to come up with an exact Z-score. I'm selling you on the feeling of this, the feeling meaning that you can understand what these numbers mean. And then Z-scoring will come up soon. So that's all I have for you for now. So thank you for making it this far, right? You know how I end things. Thank you for paying attention and not taking too many notes and just kind of listening and trying to get the feeling of what we're doing here. I bid you all safety, love, and happiness. All get along. Don't yell at each other. And everyone have a great rest of the day. Bye-bye.